All right? Can you hear me? Okay, I hope it's on. So, as you may have noticed, this topic is about mathematics. Okay? And as a nerd, maybe, I would say this lecture or this speech would contain things from what you have already know from primary school to things that you will never perceive as a human being or as a three-dimensional creature. So let's start with the primary school thing. What comes up to your mind when we talk about primary school? Perhaps that is the blackboard, all right? And I do miss the days that I can mess up this blackboard thing. I can write things on it and I can erase it. I can do whatever I want with this board. And now I'm doing a lecture. That's cool. And today we talk about dimensions. Let's start with this. What's that? What do you think is that? It's a dot, right? Okay, a dot is actually zero-dimensional object. It has no measurement, no length, no width, not everything. Okay, so then we move on to this. This is a line, okay, an ugly line. Maybe I can sort of clean it up a little bit, or maybe not. Then this is a line, it's a one-dimensional object. It has direction and it has a length. Okay, and I got a really bad drawing. I'm sorry, Tamash. So in this case, I would say I skipped this thing to draw on my own, but rather I let it to do it for me. We have passed the 0 and 1 dimensions, and now let's go to a 2 or 3 dimensional thing that is what we are more familiar with. This happened to be a square, and this happened to be a cube. Okay, it's spinning. And actually, the board is 2D even if you're wearing your glasses. And this thing is rotating, but we kind of think it's 3D because I have projected everything onto this board. So you may notice that the squares are no longer square, even if in 3D space it's a regular shape, and now it's distorted. You get this thing, and you need to keep that in mind if you go to a higher dimension. So, just a reminder, okay? So a zero-dimensional object, a dot, which is one dot, and a line is two dots. So two-dimensional regular shape would be a triangle which contains 3 dots. And this is called the 3-simplex, and it's the regular 3-dimensional object. 4 dots, all the edges are same, all the triangles are regular triangles, and the shape, what we call a simplex, means it's the simplest regular shape. And maybe we can sort of make use of this stereo projection, not limit it into 2D object. We can move it actually out of the screen. Yeah, now it looks much better. After this, we can go for next step, which is the 4-dimensional thing. We have already think about this, so just make a guess how many dots would there be for a 4-dimensional simplex. 5, right? And all the edges should be the same. And all the triangles should be regular triangle. And all the 4 dots should make a 3-simplex. And this is the simplest 4D object in whatever 4-dimensional world we have. What a pity that we cannot perceive it. And what we see here is a 3D projection from the actual object, since we don't have the capability of directly looking at it. So, we have already known this one, the simplex, and now here comes to this one. If we go from a cube, we got what is called a hypercube. It contains 8 cubes, and all the cubes are the same, and they have same dimensions, same measurements, same shape, all the same, and let's put it here. And those are other four-dimensional jewelries or four-dimensional geometries. If it's not interesting to you, yeah, let's just put it here. The one on your right would be something called the 24 cells. It's called 24 cells because it contains 24 3D cells, of course, and this is the 16 cells. Take a big look at this one, the hypercube. When I'm dragging it, I'm actually rotating this along its fourth dimension. You're thinking, yeah, if I rotate it into a correct orientation, then you might think that's a cube. Let's see if I can find it. Yeah, almost there. Then in that case, just like when you're looking at a cube is in front of you, you look at like a square, right? But actually, it's not. It's just rotating. Then it comes to this one, the 24 cell. 19.8 vertices, 1,200 edges, and they're all the same. They're not in this projection, but just imagine if it's in a higher dimension. Let's take a closer look of it. Or we can even go into this structure. The complexity and the diversity of this, they're all basically tetrahedron as a cell, and it contains 24 of them. Every cell has 12 vertices, and altogether, like this.